M1 Dynamics, example 5. We've got a situation here where we've got a small pebble attached to the end of a string, and we've got to find the tension in the string under various circumstances. The first thing to notice is that the particle weighs 500 grams. Now you've got to remember that the mass is measured in kilograms. So 500 grams is half a kilogram. So the mass is 0.5. But when we label our diagrams, we're putting forces on the diagram. And if you remember from example 1, weight is the mass times g, which is 0.5 g in this case. So on each of the diagrams, I've put 0.5 g as the weight of the particle acting down, and then the tension in the string is the thing that stops the particle or the pebble falling to the ground. So we've got 4 different scenarios. For acceleration, I use a double-headed arrow like this. So the first one, we're moving upwards with an acceleration of 2 meters per second squared. So I've drawn the picture here, and I've drawn the arrow to indicate the direction of motion. So in each case, we're going to be using F equals ma, and we're going to do it in the direction of motion. So for the first one, going upwards, we have t minus 0.5 g equals m, the mass, times the acceleration. So if you work that out on your calculator, bring the 0.5 g over to the right hand side, that works out to be 5.9 newtons. So just check that you can get that one. Why not pause the video at this point and see if you can work out the answers to the other 3, and then come back and check and see if you've got them right. So for part B, the object is moving downwards with an acceleration of 3. So doing F equals ma in the direction of motion, 0.5 g is pulling down, the tension is resisting motion, the mass is 0.5, and the acceleration is 3. So 0.5 g minus, this comes to 1.5, so bring that over to the left, and I'll bring the t over to the right to make it positive. So calculating that, we get t equals 3.4 newtons. For part C, we have a situation where the 2 forces balance out. There's no acceleration. I've done it going downwards, but I could have done it going upwards. It wouldn't make any difference because the acceleration is 0, but the question indicated it was going downwards at a constant speed. Constant speed, constant velocity means no acceleration. So here we have 0.5 g minus t is the mass times the acceleration, which is 0. In other words, 0.5 g is equal to t. Half of 9.8 is 4.9. Final question. This is moving downwards with a deceleration, sometimes called a retardation, a slowing down. So we'd have 0.5 g minus t, mass times acceleration. And if you rearrange the algebra, t works out to be 6.9.